Welcome to this lecture on rare earths as the heartbeat of modern chips, where we'll explore why a handful of elements matter so much to advanced computing. Over the next sections, I'll explain their unique chemistry, how they improve semiconductors, the supply risks we face, and the practical steps to secure and recycle these critical materials for future technologies. The rare earth family actually includes 17 elements, from scandium and yttrium through the lanthanides, and despite their name, they are widely dispersed, which makes extraction complex. What gives them power is the 4F electron shell, which enables tunable conductivity, vivid luminescence, and strong magnetism that designers exploit across electronics and photonics. Rare earth ion doping means inserting tiny concentrations of these elements into silicon, GaN, or SiC lattices to tune material behavior. Practically, this absorbs impurities, engineers band gaps, and boosts electron mobility, which translates into transistors that switch faster, lasers that emit purer wavelengths, and sensors that operate at higher temperatures with lower noise. Here you can see rare earths in action at the chip scale. Neodymium and dysprosium enable high U-coercivity nanoscale magnets for on-chip inductors, microactuators, and spintronic interconnects, while ytterbium ions power trapped ion quantum processors by creating exceptionally stable qubits that push computing beyond classical limits. In optoelectronics, europium, terbium, and yttrium act as phosphors to generate red, green, and blue emission with near-perfect color purity. When electrical signals become photons, these rare earths enable micro-CLED displays, high-speed optical data links, and Labhauser-chip sensors, unlocking advanced visual technologies, faster communication, and precision sensing. There is a strategic choke point in the global supply chain because a small number of countries dominate mining and refining. With around 70% of mined output and 90% of refining concentrated, export controls can act like an oil tap and threaten defense, AI, telecom, and critical infrastructure by exposing them to sudden shortages. Supply chain vulnerabilities arise across 4 areas: raw material complexity with low-grade ores and byproducts, energy and water, intensive processing and refining, ESG, and operational risks that raise costs and lead times, and market barriers from high entry costs and geopolitics that discourage new entrants and concentrate supply despite rising demand. Turning to solutions, advanced EC waste recovery uses hydrometallurgical and molten salt processes to reclaim rare earths from spent phones, HDDs, and motors. By leaching, electrolysis, and refining these flows can recover significant lanthanum and neodymium fractions, reducing landfill, lowering carbon footprints, and easing dependence on primary imports. Closed-eddy-loop supply chains start with easier package redesign for disassembly, move through material innovation like bulk composites and rare earth thin films to improve efficiency, and add tracking with blockchain passports to tag elements and meet EU recycling quotas, creating traceable, circular flows that keep materials in use longer and compliant. Demand for rare earths is being driven by AI accelerators, quantum processors, micro-G LED displays, and 5G RF front-ends, and projections suggest annual demand could reach about 160,000 tons by 2026, driven by advanced semiconductors. Meeting that need requires doubling recycling rates and building new non-EU Chinese refining capacity within a few years. Innovation is happening across extraction and chip technology, from AI-guided ore sorting and satellite-old exploration to solvent-free ionic liquid refining that promises lower environmental impact, while on the device side, europium-doped GaN and ytterbium photonic qubits offer pathways to room temperature, quantum chips, and ultra-efficient photonics at lower cost. Securing the rare earth supply chain demands collective action. Diversify supply contracts to mitigate geopolitical risk, invest in recycling and recovery infrastructure, co-design chips for easy disassembly and recyclability, and align policy incentives and funding for domestic refining. Taken together, these steps help ensure the rare earth heartbeat of tomorrow's chips keeps beating.